All right. I have spent all afternoon doing some research. Today we will examine some factoring problems that are what people would normally think of when they think, oh, I got to do algebra. And students worldwide hate these problems. Well, some of them they find interesting because they're very doable. Other ones, forget about it. They can be very hard. And I have several strategies that make them be not hard at all. And I was working on a brand new one this afternoon, and I am really tempted to try it out here because it is pretty darn easy. But we'll see how it goes. So, factoring is what we're doing today. Let's start off with some definitions. So a number like this one here, n, if it is equal to this product, then it is said to have factors A and B. You can contrast this with what it looked like when it was a sum. If some number was A plus B, then that number is said to be the sum of terms. A and B. The point here is that if it's two things being added, or any number of things, these guys are terms. The terms are separated by the plus sign. And if it's a product, then they're factors. Terms, factors. In math, a theorem is not up for debate. If it's a theorem, then it has been shown to be irrefutably true. And most of the branches have a fundamental theorem. Fundamental theorem of arithmetic, fundamental theorem of algebra, fundamental theorem of calculus, fundamental theorem of whatever. And we should know, or we don't know yet, but we are about to know, you are about to find out, what is the fundamental theorem of arithmetic. Because we will use it. It says that every integer, let me say it like this, every positive integer is constructed from prime factors. Now this is actually a big deal, because it is not at the foundational level, it is not exactly true that we built all of the integers by just adding 1. Way back in the day, like 1,000 some odd years ago, there was a guy named Piano that tried to show that that was the case. Said that there's a number called 1, and that all the numbers have an immediate successor, and all the numbers except for 1 have an immediate predecessor. And that was the reigning theory for a long time, until I guess like the 1600s, when it was more accurately stated in terms of prime numbers. Now you know what the prime numbers are, right? What are some examples? 1 is not prime. 1 is the unity. It is the unit. Prime numbers are always greater than 1. I'll tell you the first prime number. It's unique because it's the only even prime number, and that's 2. What would be the next prime number? What does it even mean to be prime?
It can only be divisible by itself.
Talk to me about in terms of factors. Because when we say divisible, really you're meaning it's evenly divisible with no remainder, right? And divisibility is always in terms of a product, right? If 6 is evenly divisible by 3, it happens to be 2, but this is only because 6 is 3 times 2. 6 has factors of 3 and 2. right? Now, if I plopped down the number 7 and wanted to talk about some kind of factorization of 7, the only choice is this, modulo, that you can do it in whatever order. That doesn't count as a different factorization. So this is what it means to be prime. A prime number has as its only factorization this. That's all you can do. It has, so, and because it's multiplied by 1, 1 is the multiplicative identity, it might as well not even be written there. So you can say that prime numbers can't be factored any further. That's it. Once it's, once you have, here is 6. 6 is not prime because I have factored it into these two other numbers, each of which is a prime number. 3 is prime, 2 is prime. So I guess we now have our next prime on this list. It's 3. Okay, is 4 prime? No, because it's 2 times 2. 2 is a prime number, and 4 is assembled. It's created from this product of 2 prime numbers. What about 5? 5 is prime. 6 is not. 7 is prime. 8 is not. 8 is 2 times 2 times 2. 9, that's 3 squared. 10, that's 2 times 5. 2 and 5 are both primes. These are the prime numbers. There's an infinite number of prime numbers. And what we were deducing, here is the attendance code. What we were deducing was that every positive integer can be written as this product of prime numbers. Not just that it can be written as a product of prime numbers, but that if we both picked an integer, or excuse me, if somebody gave us an integer and you factored it as a product of prime numbers and I also factored it as a product of prime numbers, we would have the same factorization. It's unique. There's only one way to do it. So a good example, I guess, is 60. The whole reason that, like, our hours, minutes, minutes and seconds goes by 60 is because 60 can be factored a lot of different ways. The Egyptians used to, way back when, used to use a monetary system that was base 60 because it was easy to make change in the markets. So let's factor 60 into a product of prime numbers. All right, I'll get us started. 6 times 10. There. I have written 60 as this product. It has 2 factors now, 6 and 10. But I want to keep going until it's nothing but primes. All right? So how does 6 factor now? Okay. And 10 would be? Then I can write this compactly as 2 squared times 3 times 5. And when there's no exponent right there, it's just a 1, right? The 1 indicating that there's just one of these things. In the same way that this exponent of 2 says I have 2 of the 2's. All right. Um, okay, here's another example. 42. I want the prime factorization of 42. So how does it factor at all? Huh? So, Rosalinda, don't try and do the whole thing at once, I guess is what I mean to say. Break it into two pieces, and then you've broken it into two simpler problems, right? I mean, unless you can just see it all straight away, right? Because it would be 2 times 3 times 7, wouldn't it? And I'll put a 1 up here, because there's just one of each of those. And no matter what integer you pick, you will be able to have it as a product of prime numbers. In fact, allow me to write it in an even more goofy way. This one is 2 squared times 3 to the 1. It's got 1, 5, and it has no 7s, right? Just in the same way it doesn't have any 11s, and so on. All the rest of the exponents are 0 for all of the prime numbers, for which there's an infinite amount of. And I could do the same thing on this other one. 2 to the 1 times 3 to the 1 times 7 times 5 to the 0 times 7 to the 1 times 11 to the 0 times, and so on. So this product here, where it has just all the rest of the prime numbers with zeros for exponents, this is just 42. And this one is 60. Now they have some overlap, don't they? This one has a 2, and that one has some 2s, 3s, 3s. This one doesn't have any 5s, but and this one, and then this one doesn't have any 7s, right? And then both of them don't have any 11s, and so on. This gives rise to the concept of the greatest common factor, the GCF. Now, we already said that each of these things were factors. They're primes, but they're prime factors. So each of these are factors. They're separated by the multiplication. And this one's factored, and this one's factored. And they have some common factors. The 2s are common, the 3s are common, and that's all the common factors. Then the greatest of the common factors even though I use that word greatest, the greatest common factors is found by looking at the lowest exponent. If I intend to come over here and construct the greatest common factor of 60 and 42, then I should look at this factored forms and ask, well, the 2 is common. The 2 is a common factor. And what is the greatest amount of 2's that they can both give me? Huh? Only one. This one can give me a 2 because it's got a 1 for an exponent. This one can give me 1, 2 as well, but I can't get 2 of these 2's from this guy. He's only got 1 to give. So then my GCF will have 2's as a factor, but I can only squeeze 1 out of this pairing. And then it's easy on the 3's because they both have 1 3 to donate. I look at the 5's. I can't get, this one doesn't have any 5's to give, even though that one did. So I'm not going, my GCF's not going to have any 5's. So this is a common factor, and it happens to be the greatest of all the common factors. And it's just constructed from the prime factorization. I looked at its factorization of each number, and I literally went through each one and used the least exponent. 2 to the 1, 3 to the 1. Then I would have, if I look at the 5's, among these two 5's, which exponent's lower, 1 or 0? So it's going to have a 5 to the 0 in my GCF. For the 7's, what is the lowest exponent?
0.
And so on. And this is how the GCF is constructed, like behind the scenes. Is there a way to recognize what it would be more quickly? Sure. Look right here, I mean. But that's not the point. There are occasions, plenty of occasions, when it is easy to recognize what the greatest common factor would be. But then there are times when the numbers are kind of weird, big, and you're just not convinced that you have the greatest common factor. But if you use this strategy, you can absolutely convince yourself that you have every common factor assembled together to form the greatest of all the common factors. You know, because someone may have said, oh, 60, that's 2 times 30. They may have looked at 42 and said, oh, yeah, I know that, that's 2 times 21. And then talk themselves into saying, oh, well, the GCF is 2, not really realizing that 21 and 30 also have a common factor. It's easy to see here, 21 and 30, they're both divisible by 3. But if the numbers are like 400 something, it's going to be harder. And so you may need such a strategy to fall back to. I can tell you already where I know you would absolutely use this strategy. Notice that these are already factored, right? They're already a product of things. And if I wanted to know about which factors were common among, here, let me go like this. This one says X, Y, Z. If I wanted to talk about which factors were common, so that I could find the greatest common factor, then gee whiz, isn't this exactly the same strategy we were just doing when we took a number, wrote it as its prime factorization into a product of prime numbers, and then went through pairwise and said, okay, what about the x's? Which exponent is the lowest? And it would be the 3. So my GCF would have to be able, my GCF would get 3 x's. Okay, and then I would say, well, what about the y's? What's the lowest exponent? Well, it's a 1. So my GCF would have the 1 y. And then what about z's? Which exponent is the lowest? Well, 0. So my GCF's not going to have any z's. There's my GCF. Probably more commonly written as x cubed times y. So the point here is to realize that I don't specifically know what numbers x, y, and z are. But there's really no reason that they can't be 2, 3, and 5. And they're just symbols at the end of the day. 2, 3, and 5 are symbols, just like x, y, and z are symbols. And if you want to produce the GCF of a bunch of symbols, those strategies are the same. There's not a special one for numbers and a different one for variables. It's just the one strategy for symbols. And numbers happen to be symbols. So factoring is the name of the game. The C is for common. We want factors which are common to both of them. Of course, if it's a prime, if I have this idea that z to the 0 is just, there's no zeros. What number is this, by the way? 1. And then, this word common is kind of extraneous. It's just the greatest factor. I got factors. What's the greatest amount of factors that I can get out of this parrot? Okay. Where would we use this? There's each of those two things we were just looking at, and now they're added together. And we already identified that the greatest common factor was x cubed y. So I can rewrite this so that I witness that greatest common factor kind of separated from the rest of the riffraff. Right? I took my x to the 4th y squared, and look, now it's factored. It's factored with the GCF times the other stuff. And then I did the same thing here. This is now, it already was factored, but now I've just put these parentheses here to kind of show just a factoring into these two things, the GCF and the other stuff. What is the name of the property that I now want to use to simplify this? Because here it is, it's a sum of terms, but I want it to be a product of two factors. And what sort of property could I use? The distributive property. The distributive property says that, if that has the role of the A, and this has the role of the B, and this has the role of the C, then that A factors out, and you're left with the other factor being B plus C. So my A would factor out, and then what would have to be left over is B plus C. And now we have a product. You have this, the GCF, times the other stuff. It's a product of two things. It's factored. It's factored. I took this sum of terms and factored it. So this concept of rewriting some sum of terms by factoring out the GCF is one of the factoring requirements of the day. After that, so there's several problems on the homework dealing with that. We'll do those in a second. They're straightforward. Oh, let me also say, the discussion board is a video problem about how do I obtain the GCF, identifying the GCF. Okay. If you get to your video, if when making your video, you try and tell me that you used one technique for the numbers and a different one for the letters, I will cringe. I will grit my teeth and slap my hands on the desk. No. They are the exact same strategy, whether it's for the numbers, whether it's over here. It's the same thing. Any shortcuts that you may do, like for example here, when we could have realized, oh, 6 is going to be our GCF, because I can see that 10 and 7 don't have any common factors. On that same token, you could have realized that this thing was x to the cube y times xy, and then said, oh, this must be the GCF because these guys don't have any common factors. You are doing the same thing in either situation. Numbers, variables. Variables are numbers. They're just numbers that we don't know what they are exactly yet. They can be whatever you want. So, I would avoid this talk of, I have my one strategy for the variables and I have this other strategy for the numbers. I would avoid any talk of divisibility. Always phrase it from the perspective of writing products, writing products. While you can write a whole bunch of algebra that uses all kinds of divisibility, you're wasting your time and you're missing the point. So, on the discussion board, they want you to produce some expression and then show how to get the greatest common factor. And it probably also says to go ahead and factor out that greatest common factor. So here's the type of example that I would come up with. Nothing too difficult, but not the very simplest one that you can conceive of. So let's do 3x squared plus 9xy. There. Now, on the one hand, if these numbers are very small. I'm not going to have to resort to a bunch of big long string of prime factorization. But by that strategy, you would be recognizing that the first term was this, and the second term is this. This says 3x squared. This says 9xy. And look at how they look identical. Both terms have 3's, both terms have x's, and both terms have y's. It's just the exponents that are different. And if the exponent's 0, that term's not really there. It's just times 1. Then I can easily figure out what my GCF is by going factor by factor and getting the one with the least exponent. So for the 3's, the least exponent is 1. For the x's, the least exponent is 1. And for the y's, the least exponent is 0. That's my greatest common factor. Now this is my ultimate thinking of how to do it. Obviously, I'm not going to write y to the 0 or these 1s. So then here is my GCF. Alternately, the other, it's not even a different way. It's just the shortcut. It's the oh, I see what the GCF is, and I did not have to bust it all the way down into prime factorization. You would have, I would see, oh, that first term is 3x times x, and the other one looks like 3x times 3y. This is, so 3x squared, that's here. 9xy, that's here. And look at how they both have a 3x. And I know that the GCF must be 3x because x and 3y don't have any common factors. Now, unless the numbers are particularly offensive to look at, this is probably the preferred way to do it. No sense in taking extra time to do something. However, if the numbers are goofy, and you need to be absolutely sure for whatever reason, then the top strategy is where it's at. It just absolutely will never give you the wrong answer. It will always hand deliver to you the entire GCF. Okay, let's look at some of the homework problems. You will find them to be very easy. This one seems like a great discussion board problem. Right? Don't have to make it too hard. However, if it was just, let me tell you what would be inappropriate that I have seen students try and do 4a minus 24. This is too easy. Right? So here we tossed in an A. They both have A's, and they both have 4's as factors. even though 4 is not prime, we're using that alternate shortcut technique where I don't have to bust everything down to its prime factorization. So the first term says 4a times a, and the second term says 4a times 6. Then I know that 4a must be the GCF because a and 6 don't have any common factors. So 4a is my GCF. Then by the which property? By the distributive property, the 4a will factor out, and what's left over is the a minus 6. Okay? All right. Now we've got this monster, and I know that 21 is 3 times 7, and I know that 42 is 6 times 7. So I think I can get that GCF straight away, because this would be 7x to the 6th times 3 minus 7x to the 6th times 6x plus 7x to the 6th times x squared. It's a good strategy for you to make this intermediate step. Even if you could recognize, oh, the GCF is 7x squared, it pays to write this step, because I can witness that each term has a 7x to the 6th. I can see that the first term does compute to be 21x squared, that the second term computes to be this, and so on. So I know I have everything factored correctly. And I can also be reassured that I have the greatest common factor, because 3 and 6x and x squared don't all share any common factors. Then, by the distributive property, the 7x to the 6th is out front, and you can easily see the stuff that's left over. It's all the symbols I'm pointing at with the arrows. So 3 minus 6x plus x squared. Questions? Ready for the next one? Are we ready for the next one? Yeah. Starting to get wild looking. You just got to think about like as if this term here is just some number. And that 20, I mean, if I had it written as its prime factor, so here's what I'm saying. This is some number who's ultimately who has a prime factorization that's got 5 A's and 5 B's in it. So you can just use that same idea. We don't have to say, oh, I need to handle this number separately from this part. No, each term is a number, and it has factors of A and B in some differing quantity. I know, just at a glance, you would know that the 35 and the 20 have a prime factor of 5. And that ultimately, my GCF is at least going to have this 5. Well, at least is the wrong word. The GCF could not have any other integer than 5 in it. Because however 35 factors, so 35, 5 times 7, there ain't no 7s over here. Just in the same way that if this one had a C, there are not any C's over here. And this one's 4 times 5. And that one doesn't have any 4s, and this one doesn't have any 4s. 4 is not going to be in my GCF. I'm only going to have a 5. I'm going to have some amount of 5s, some amount of A's, and some amount of B's. And since there's just the 1 5 to contribute, I just have the 1 5 for my GCF. And at a glance, now, among the A's, you can see that you're only going to be able to squeeze 2 out of them, out of each of them. That's the most that A's that you can get out of all 3 of those, is 2 A's. Because 2 is the least of the exponents among the A's. And the least of the exponents among the B's is this 4. So then, hey, the GCF is this whole term here. Because I can only get a 5, I can only get an A squared, and I can only get a B to the 4th out of everything. So, I will rewrite all my terms as the GCF times the stuff that's left over right there. This is exactly that. It says 20, and then there's 4 A's, because I would add the 5 A's, because I would add the exponents, and there's 5 B's, because I would add the exponents. So there's my first term rewritten, and the second term rewritten would be, well, here's my GCF. And then you would have 7 times B squared. Because if you simplified that all down, you'd have 7 times 5, that's 35, times A squared times B to the 6th. And that's what this number is. And then over here, here's my GCF, 5A squared B to the 4th. And just so I can have something to write that will help me, I guess, not have this place in my mind where there's a special case. It's just the exact same strategy everywhere, but a 1. Then I'm not having to think about, oh, there's a special case going on or whatever. No, we'd be doing the identical thing to the previous problem. I've got a GCF times the other stuff. GCF, other stuff, GCF, other stuff. You can always stick a 1 there. So now I can pull that GCF out. And then to fill out the rest of it, I am just reading what I already wrote and copying it right back down. I've already verified that it's all correct. So like, here would be a common, so in many algebra classes, the instructor would say something like, okay, here's our GCF, and then I get all this stuff written here, and then now let me check if I did it right. And they want to distribute it back in. That's a waste of time. If you have this written, you've already checked that it's correct. Because here's my GCF, here's my GCF, and here's my GCF. And each of these terms matches up with each of those terms. When I go to rewrite it right here, 4a cubed b minus 7b squared plus 1, it's right. And there's nothing to check. I mean, you can check it if you want, but are you really going to be surprised that it came out the same as it should have? You would have double checked by that point. You checked here and then you checked again. Any questions? Ready for the next one? All right, so, it was like, easy, medium, hard. They gave you an easy one, a medium one, and a hard one. And then now they're done with the problems where you are purely factoring out the greatest common factor. But now we will continue to use this idea of, can I see what is the greatest common factor in other scenarios? At the beginning of the class, I said that I have this other fantastic technique. So the whole reason to study this type of problem, where you factor by grouping, is so that you can then use it later on in a harder problem. But on those harder problems, I've avoided this altogether. But we will cover both strategies because they're both good. So, to factor by grouping, you'll know that you have to factor by grouping because there's an even number of terms you always want to form some, well, is even the right word? There's definitely more than 3 terms, or you can't form 2 groups, right? So more than 3 terms. And the GCF is 1. Meaning that when you look at all of those terms, let's say there's 4 terms. When you're looking at all 4 terms, the biggest number that can be factored out of all 4 of them is just 1. Now, here, just take this one as an example. Verify, it's got more than 3 terms, right? It's got 4. What's the GCF? It's got to be, this guy doesn't have any D's. This guy doesn't have any D's. That one doesn't have an H. This one doesn't have a 3 or a 2. No 2, no 3. That's everything, right? In other words, I'm looking, all that gibberish I just said was that the first term is 2 to the 1 times 3 squared times d to the 1 times h to the 0 times s to the 0, because 2, 3, d, h, and s are all of the terms that are being used in this thing. And just that this first term doesn't have any h's or s's. And the second one doesn't have any 3's, and it doesn't have any d's, and it doesn't have any s's. Like, you don't need to write this part down. It's for illustration only. I could keep going. But I know that the GCF must be 1 because if I went through and did this on, looked at all of the terms on all 4 of those, I'd come back with nothing. For each term, there's at least one of 2, 3, d, h, and s that has a 0 for an exponent. That's the message. So we end up with a GCF of 0. There's nothing that I can get out of all 4 of those terms. Here comes the grouping part. It doesn't matter how you group them. You should just group them right, just the way it sits. Just take the first 2 and stick some parentheses around it. Take the second 2, stick parentheses around it. Well, let me rephrase. The only stipulation about how you should group it is that each of the groups should then have a GCF different from 1. So right here in this parentheses, I have a GCF of 2. And over here I have a GCF of s. So I can factor out the GCFs from each grouping. So when I pull out the 2, I'm left with 9d plus h. And when I pull out the s, oh, well, would you look at that? I'm left with 9d plus h. I started off with 4 terms, 1, 2, 3, 4. I grouped them. I pulled the GCFs out of the groups. Now I have only 2 terms. You have this term, and then here's plus, and then you have this other term. And each of those 2 terms are factored, and don't they have a common factor? This term and this term, what do they have in common? Yeah, that stuff in parentheses, the 9d plus h. It looks just like what we were doing in the previous problems, where I've got my sum of terms and I have the GCF like witnessed. And so I can see exactly what's going to be left over, 2 plus s. So I'll factor out my 9d plus h, and then what's left over is 2 plus s. It started off as a sum, now it's a product. Questions? Let's take our break. It's 7:10 right now. We'll come back at 7:20. And there's just the one more factor by grouping question. We'll do it, and then on to the real stuff. Or not the real stuff, but it'll be suddenly harder. It'll be suddenly harder unless I've done my job good and figured out a way to make it easy for you. Were you copying something down?
No, it's just moved up so I can see.
Oh, okay. Is that all right, too small?
No, I couldn't see the problem.
Oh, okay. Sometimes I have to make it smaller because the answer box gets in the way. And plus they have all this wasted space up here. It's really a pain. All right. Factor by group. In most cases, if you're given the problem, the groups are ready to go, where you can just, so what am I saying? You can just put the parentheses right here. Right? You can group it right like it sits. All right. Well, we didn't verify before we started. No common factor. No common factor, so ipso facto, no greatest common factor. And more than 3 terms. So factor by grouping is what you would do even in the absence of these instructions. And in the first grouping, now I have a GCF. It's x squared. What's left over would be x plus 9. And in the second grouping, a 3 has got to factor out. In fact, when you are factoring by grouping, the ultimate goal is that when you arrive at this stage, that each term have the very same thing in parentheses there. Like, we're wasting our time if we factor by grouping and get stuck here to where now these 2 terms don't have a GCF. But they do, and the GCF is x plus 9. So the x plus 9 will factor out, and what's left over will be x squared plus 3. Questions?
Can I start writing x squared plus 3 and then x plus 9? Will it be right now?
Yeah. Why would that be right? It's for the same reason that, 5 times 3 is 3 times 5. It's called commutativity. Yeah. Yeah. You can switch these so it is equivalent to say this. Note here that the x squared plus 3 does not factor any further. Right? Even if it had said x squared plus 4, that does not factor any further, not in the real numbers. But something like x squared minus 4 certainly would, right? It's a difference of two squares. It factors into a conjugate pair. There is no such thing as a sum of two squares. And even though 3 is not a perfect square, I could always just write square root of 3. But because it's a sum, it ain't gonna factor. Factor the trinomial. They could have used a better word like quadratic. There are lots of things that are trinomials. When we were doing like question 3, that was a trinomial. Right? Trinomial just meaning it's got 3 terms. It's got 3 terms. This is a trinomial. 1, 2, 3. But it is not a quadratic. A quadratic specifically has its highest exponent 2. Right? It's quadratic because when they came up with that name, this described the area of some 4-sided rectangle, or all rectangle. It described the area of some rectangle. This is the area of some rectangle, and I would sure like to know the length and the width. That's the factorization. If I can factor it into two things, L and W multiplied together is the area. So if I can get this thing written like a product of two things, then you can really, reason out then that there's my area and it's length times width. That's why they are calling it quadratic. Okay, now, everybody has at least computer or calculator. True? I do not recommend your phone calculator, but there's a way around it. You can use your browser and go to Google, which is exactly what I will do here. And I will type calculator and get the Google calculator. Why do I want this? Because it has the answer button. If your calculator has the answer button, then it will work for what we're trying to do. Otherwise, I would recommend just going here because it has the answer button. And I already checked this earlier. It does exactly what we need. All right. So this is one of the alternate factoring strategies that I was talking about that completely eliminates any of this guessing business. Why is that important? Let me view an example. Oh my God, that just boils my blood right there. They're basically telling you they're just saying, we don't know, figure it out. Stare at it, and maybe you'll come up with something, right? And I hate that. Because for easy problems, it's doable. But they have plenty of problems that are not. You can stare at it all day, you're not going to figure it out. And so, here is one strategy. We'll do this a couple of ways. It's b squared plus 7b minus 18. Now, I want to put this equal to 0. Because ultimately what this is all about is we've got some curve. This makes some curve in the plane. And here, if I put this as y, or a, or whatever, then it would be in the A-B plane, and it makes some kind of curve. And it has these two places where it crosses the B-axis. If it's going to cross the B-axis, then that's where A is 0. So I'll just put the 0 for the A. Now, we're going to use a strategy called iteration. Put the 18 on the other side. Because when I'm looking at these three terms, the GCF is 1. I can't factor anything out. I put the 18 on the other side. Now look, I have something to factor out here, a B. The B factors out, I'm left with B plus 7. It's equal to 18. Divide both sides by the B plus 7. So that way B is equal to 18 over B plus 7. If somebody saw you doing this and didn't know where you were headed, they would say, whoa, whoa, you're screwing up, whatever. But this is exactly what we want. So the Greeks would have used a similar technique to find the value of square roots. What we're going to do is, I want to know what B is, right? If I know what B is, then I can take that number B, I put it right here, and it would have to be the case that it came out equal to 0 in this equation. And all I've done is rearrange that equation into this, in the pursuit of what is B. So, we're going to make a guess. My default guess for the day is probably 2. Every time, I'm just going to guess 2. And so I'll go to my calculator and I'll push the number 2 and I'll hit equals. And then 2 will be stored as the answer. Then I will type in 18 divided by answer plus 7. Where my initial guess was 2, and then here, it's going to take that 2 and it's going to put it right here, because 2 is the answer. I'll hit equals and I'll get some other number. In this case, it would be 18 over, well, here's a case where 2 wouldn't. So this converges immediately. 2 is not a good example for this one. Let's try 3. It converged immediately because what did I get? I got 18 over 9, which is again 2. I would just get 2 again because the point here is that I'm just going to sit here and hit equals, 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 equals over and over and over, and it's going to run this equation over and over and over again and converge on the answer. Let's try 3. It would be 18 over 10, right? Some number. It's 1.8 actually. And so then when I hit, and now 1.8 is the answer stored in the calculator's memory. And then I just hit equals again. and it will put 1.8 here. It'll be 18 over 8.8. And I hit equals again, and again, and again, and again, and again. And very quickly, I'll be able to identify what number is it converging to. So let's try. We're going to guess 3. If I had guessed 2, 2 would still work. I just would have typed it in and immediately seen that I was getting 2, no matter what. No matter how many times I press equal, it'd just be 2. So B had to be 2. All right, so 18 over answer plus 7. So my initial guess is 3. There it is, stored. Then it's 18 over, open some parentheses, because I want that whole denominator down there. Answer plus 7. Right? And I get 1.8, okay. But if I hit enter again, I get this, and I can just keep hitting enter. And look how it's telling me it's 2. Right? It marched right up to the 2. So 2 is one of the solutions. Excellent. We know, so what do we know? We know now that if B is 2, then our equation gets satisfied, because 2 squared plus 7 times 2 minus 18 really is 0. Now we'll use a very simple process called synthetic division to find the other number, because there's going to be two numbers that satisfy this equation. Always 2 numbers that satisfy this equation. Okay, so let me rewrite it. It's b squared plus 7b minus 18. You can see here what our coefficients are. Our coefficients are 1 and 7 and minus 18. And so far what we know, since 2 is one of the solutions, then the factorization would have to look like this. This part I don't know yet. And I know it's got to look like this because look what happens when I put a 2 right there. It would say 2 minus 2, which is 0. So it doesn't matter what this is, because it would be 0 times something, which is 0. And the equation would be satisfied. I have one of my solutions as 2. Put it in a little box like that. List out the other coefficients. We're going to actually perform the division. What are we going to do? We're doing this. I'm taking the original thing and not x, b. I'm dividing by b minus 2. But we're not doing long division, because that's the long way. We're doing synthetic division because it's quicker, easier, less of a headache. It works like this. You bring down the 1. You always just bring down this first number. It's the same thing every time. I bring it down. Now we'll get started. 2 times 1. 2 times 1 is 2. I'll put it here. And now I'll add. 7 plus 2, that's 9. We're rocking and rolling. Now you repeat. 2 times 9. That's 18. Minus 18 plus 18, that's 0. If we don't get a 0 here, we've done something wrong. You're guaranteed to get a 0 there. That's the remainder. The remainder is 0. See how I have a 1 and a 9? That means the coefficient on my x is 1, and then my constant is 9. This stuff up here is 1 times x plus 9, or I mean b. B minus 2 and b plus 9. Well, you can verify now all you'd like that it really does multiply together to give you this other thing. Are there easier ways? Sure, but this is an easy problem. I manipulated what I started with in such a way that it could be the variable on one side all by itself, and on the other side had the variable in the denominator. It ain't going to work unless the stuff's in the denominator. Then you can iterate over and over and over, and it told us that one of the solutions was 2. Then I actually divided out this term, this b minus 2. This right here is us performing that division. What did we find that b was? We found that b was 2. I put the 2 right there. I do the division, and now I have the coefficients for the other term. Now this strategy really shines when the problems are intractable. There is a different algorithm that I have used in the past with much success. And that's what we'll do right now. If you ever wanted to talk about why I would have to set up this other stuff this way, we can. But for now, you just accept it that if I want to know the solutions to this without having to guess and check, then it's going to be easier for me to study this system of equations. This system of equations is actually equivalent to the solutions to this problem when it's equal to 0. If I can figure out what this x and y are, then what I will do is come back to my original quadratic and rewrite that middle term using the x and the y. See that this would have to work. This is x times b plus y times b. That would have to equal 7b. And that's what this says. X plus y is 7. If you can get to this stage, look, it's got 4 terms. GCF is 1. So you would factor by grouping. Determining what the solutions are to this system can be tricky. I recommend you use the sum. Work with the sum. Write down start anywhere you want with 2 candidates that add up to 7. There, my candidates are 1 and 6. The issue is that 1 times 6 is not a negative 18. So while 1 and 6 for x and y worked here, they didn't work for the first equation. So I'll just move on to the next stage. I'll add 1 on one side and subtract 1 on the other side, right? I'll add 1 here and get 2, and subtract 1 on the other side, get 5. That's still 7. 2 times 5, though, is not negative 18. It's not even negative. What should my candidates be looking like if I'm going to have this product be negative? At least, or excuse me, exactly one of them should be negative, right? Exactly one of them should be negative. So a better starting point would then be something like 8 minus 1. That's 7. And then 8 times negative 1 is negative 8. It's not negative 18, but at least it's negative. And then you just keep going. 9 minus 2. That's 7. And, oh, look at that. 9 times negative 2 is negative 18. So I can come back over here and say that this would be b squared plus 9b minus 2b minus 18. I have uncovered what it looked like. Like suppose I had the factorization down here and I multiplied them together. Well, then I would multiply them together and get this. And then I would combine like terms and get that. So I have found out what it would have looked like if I knew how it factored and multiplied them together. I found out what it looked like before we combined like terms. So now I can factor by grouping. Because this process of factoring by grouping is exactly that repeated distribution that we use to uncover what the FOIL process really is. From these first two terms, they have a b in common. The b factors out. I'm left with b plus 9. From the next two terms, I can factor out a minus 2, and then I'm left with b plus 9. Now they both have a b plus 9 in common, so I get b minus 2 times b plus 9. So it's worth it to go through the motions on easier problems of one of these algorithms so that when the tough one comes, everything works exactly the same. It transforms all the hard problems into basic ones like this. Because if you've had algebra before, your strategy was more than likely to have been, let me look at this and factor it into all the different ways that I could factor it. Well, let's see, there's 1 and negative 18, or there's 2 and 9, and then all along the way you're checking to see if that combination of those factors as a sum results in this guy. And if it did, you knew that you had the answer. And yes, that works on easy problems. If you just fast forward a couple of problems into the homework, you'll see right away where it won't work. We got the same thing here. I did a lot less writing. All right, the calculator delivered to me the 2, and I did synthetic division to get the other one. All right, next one. I want the solutions to this equation. The values of W that make it go, that make it work, that make it true. Our calculator can give us one of them pretty quick. I'll move the 18 to the other side. W squared plus 9W. I can factor out a W now. And so I know by dividing both sides by W plus 9 that I can form this iterative function where it's solved for one of the W's and on the other side has the W term in the denominator. I'll make an initial guess of 2. That way the answer in the calculator is 2. You could put 3 or 0 or 1, or the only thing you can't put is minus 9. Right? Because it would have an error when it started. And then in my calculator, I would type minus 18 over answer plus 9. And I would just hit the equals button over and over until it converged to some point. And that's one of the solutions. Okay? Minus 18 over answer plus 9. So it's going to tell me a minus 18 divided by 11. I don't even know what that is. It's some number. Right? It's this. But then now, when I hit equals again, it's going to use that number instead of the 2 that I had originally guessed. Because the more you repeat this, the better the guess is. Now it's guessing this. What do you think? What do you think it is? Negative 3. And finally, I'll get so many digits that that's all it can write is negative 3. So if my initial guess had been negative 3, it would have converged straight away. It would have just said negative 3 forever. Just like the same way I'm sitting here hitting equals again and again, and it just keeps saying negative 3. So negative 3 is one of the W's that satisfies this equation. All right, I've got one of them. So I should take that negative 3, put it in the little corner box, and then list out the coefficients of my original polynomial, or quadratic. You can see that they're 1, 9, and 18. Then the synthetic division says I just bring down my 1. There it is. 1 times negative 3. That's negative 3. I write it right there. 9 plus negative 3, that's 6. 6 times negative 3, that's negative 18. 18 minus 18 is 0. I have a remainder of 0, and I can see that the other term looks like x plus 6. So one of the one of the factors to this is x plus 6, and the other factor to this is, not x, w. W plus 6, and the other one is w plus 3, right? Because I would want to take this solution I have for w here and make it equal to 0. It would say w plus 3 equals 0. Well, that's what we wanted. We wanted this to be 0. And just like this one down here would say w plus 6, that means that if w was minus 6, that's the other solution to this. A minus 6 squared, that's 36. 36 plus, what's 9 times 6? Negative 54. So 36 minus 54 plus 18. 36 minus 54 plus 18, 0. So the two solutions for w are minus 3 and minus 6. So consequently, my factorization would be w plus 3 times w plus 6. Alternately, I've got this quadratic. I look at it for 5 seconds, and if I can't figure it out, I go straight to this technique. The product of two numbers is the leading coefficient times the constant. So 1 times 18. The x plus y is the number in the middle, the 9. That's where the 18 and the 9 are coming from. The 18, be careful here, the 18 is not, so the x times y is not just this number. It's this number times this coefficient out front. Because here in a minute, that coefficient out front's not going to be 1 anymore, and that's when they get fun. All right. Some candidates for x and y that add up to 9. 1 plus 8. That adds up to 9. And 1 times 8 is just 8. It's not 18, though. So I have to keep going. 2 plus 7, that's 9. 2 times 7, that's 14. It's bigger than 8, right? But it's not 18. So I have to keep going. 3 plus 6, that's 9. 3 times 6, here we are. The system has told me that I should rewrite that middle term as 3w plus 6w. And then now factor by grouping. The first pair, I can factor out a w, and I'm left with w plus 3. It is without a doubt, you will end up with a w plus 3 over here. You must. Because it will factor, this polynomial will factor, and the only way we would be able to proceed all the way to the end is if they both did have the w plus 3. So you can, in a way, let that guide you as to what would need to be factored out here. And that's a 6. All right, now they both have a w plus 3 in common. And we're done. There it is, factored. And it's the same as we got in the previous problem. Now, if you're really on top of it, you would have noticed that, hey, you got 3 and 6 as your solutions to that system, and then this is 3 and 6 over here. And the same thing happened in the previous. We got a 9 and a -2, and look, it's 9 and -2. But that will only happen when the leading coefficient is 1. If it's different from 1, that won't happen. Okay? All right, so it's W plus 3 times W plus 6. All right, here, let's try the calculator method first. You're going to see something interesting happen. In this one, it won't converge like in the other ones. It'll just bounce around to all these crazy numbers, and that will be an indicator of something. So I want to look at this as being equal to 0. Then I would have v squared minus 2v equals to -9. Just move the 9 to the other side. Well, then I can factor out v. And divide both sides by the v minus 2. So that way v is a -9 over v minus 2. -9 over v minus 2. So when I go to my calculator, I'll do my initial guess. Well, my initial guess can't be 2 here, right? Because if I tried 2, it's going to have a divide by 0 error. So I'll just need to pick some other guess. It doesn't matter what. Like, it literally doesn't matter. Pick a million, pick 10, pick 1. Here, I'll guess 1. All right, then we're going to have -9 over answer minus 2. Great. Gives me 9. Gives me this. Oh. Is it behaving like we expected? I mean, there's 4, -4, 1, 17, -0.3, -6. It's all over the place. It's not converging. It's diverging. It's not going anywhere. It's bouncing all over. And that's because, can you think why maybe that would happen? I mean, in the other ones, when we did it, it only just took a few times, and we got to what number it was going to be. It was telling us the solution. You know.
Is it because that the equation has prime numbers?
No. We got a solution in the other one because there was one. And you're not getting one here because there's not one. It's as easy as that. There isn't a number v that's going to satisfy that equation. And so this iterative procedure will just deliver all kinds of numbers. I mean, a minute ago I saw 373. It's like at each stage, this new number in the calculator is an updated guess that's supposed to be better than the previous one. But we never seem to converge to the answer, so it doesn't have one. This is a prime polynomial. It's a prime, it does not factor over the real numbers. Where was it? This has no solution. There aren't any numbers v that satisfy that equation. It's prime. And this technique, that's what'll happen. If the polynomial won't factor, then it's not going to have any v's that would satisfy this equation. Does anybody know what kind of curve this is? It's a parabola. It's a parabola. Looks like this. And in fact, it probably looks something like that. And it just does not cross the horizontal axis. It's completely above it. And that notion that it's totally above the horizontal axis, then it can never take on a value of 0 for some v. There's no values of v that make it become 0. You know, interchange the v with x, so that way it's easy. This is x squared minus 2x plus 9. Then this would be my x-axis, this would be my y-axis. There aren't any, it never crosses the x-axis, so there's no x values that give me a y value of 0. That's the geometry of it. Right? It's the exact same scenario as what I was saying earlier about something that maybe looked like this. What kind of curve is this? Nope. Exponential curves have the variable in the exponent. This is also a parabola. All parabolic curves are quadratic equations. All of them. And the graph of this one, you can easily see, if you believe that it's a parabola, then this must be it. Because if x was 0, if I put a 0 right there, it says that y has got to be 4. And that's this point. That's the point 0, 4. So it crosses the y-axis right there, but it'll never cross the x-axis. It's just completely up above it. So consequently, there is no factorization of this expression satisfying, that can satisfy such an equation, like when it's equal to 0. On the other hand, something like x squared minus 4 will cross the x-axis. In fact, it does it at minus 2 and 2. Because this guy does factor. It factors as x minus 2 times x plus 2. So you can see that the solutions to this equation, the x values that cause the y value to be 0 must be 2 and negative 2. And that's the corresponding geometry. It intersects the x-axis, so it has solutions. So prime polynomials, prime quadratics, are just parabolas that are moved up, so that way they don't cross the x-axis. take our break. Come back at 8:20 and get into some harder ones. Like this one all of a sudden. I mean, they go from here to 0 to 100 real quick.
me just go to password. Do you know which one it is? There's no, but like which one? Student internet yet? Rana, is it student
I
internet?
think it is. What's that?
I think it is this one though. We're just looking.
Yeah, student internet.
Okay.
Password.
Wi-Fi, oh, medical, all lowercase. Sorry, it was way easier than I thought it would be. I didn't expect myself to be so organized, you know? That work? That work. Thank you so much. Girl, you should have told us sooner. We'd save your life. Since like the first day of class, I'm like, how does everyone on the internet? I'm just like using it. Yeah, have you gone to the orientation? I did, but I didn't use my laptop. I used their laptop. So oh yeah, but right then you need it for like your phone or something. It's just medical 9, which you think we've memorized, but I don't forget. Yeah.
Oh, I'm trying to do the next question and remember.
I don't recommend you do it that way.
Okay.
Right? That's what we talked about earlier, that's guessing check. You'll be here all day.
So I have to use the calculator.
Why not? You can factor out an X there on the left side.
This one.
Mm-hmm.
X.
Times.
X times.
Put parentheses. No.
Oh, X times 38.
I do better.
X
X
plus,
plus 45.
and then you close
My
parentheses.
schedule does better on that,
X.
but thank you.
Equals,
Equals
okay, and then you divide both sides by the 38x plus 45. And this is equal to x.
Right? Right. I don't know.
X will be 18.
See how.
We want an x that put an equal sign. We want an x that satisfies this. Go to the calculator, put 2 as your guess,
And that's not right. I studied, but we went and had like.
equals. See how it's, okay. And put AC for all clear, top right. See how it says the answer is 2? Now you would type 18 divided by,
All I did was study, and then I can do how much you can learn. And then
open parentheses,
and then I'm gonna say.
38x plus 45. 38, answer. The answer is the x plus 45. Close parentheses. Equals. Equals. You can also just use enter. Keep going. Keep. Okay, stop. It's the same number over and over. Huh? That's one of the roots. Talk more about that in a second. Okay. So here is my next example. 51x squared plus 40x minus 75. This is where it's going to start to get noticeably more difficult. All right. So now on this one, the first time we'll do our little trick with this system of equations. The A times the B needs to be this number times this number. It's huge. 51 times minus 75. And the A plus the B is this middle coefficient, the 40. So 51 times negative 75, that's a negative 3825. And if I can figure out A and B, then I'll know how to rewrite this. I'll start by looking at the A plus B. I need two candidates that add up to 40. Those don't add up to 40. 38 and 2, 20 and 20, whatever. Are any of those going to result in a product that is negative? No. So, Carly, what do I need?
One of those to be negative.
Exactly one of A and B to be negative. So pretty much the easiest place I can start is 41 minus 1. That's 40. And 41 times negative 1 is negative 41. At least it's negative. We have a long ways to go to get to minus 3825. But we're on the right side of 0. You can, systematically make this list, and somewhere on this list is the answer. You can see it just goes on forever in both directions. Right here would be 40 minus 0. Down here is 44 minus 4. But you don't have to just go by 1. I mean, the list that's there does increment by 1. 41, 42, 43. 1, 2, 3. All the way down. But I can just kind of skip ahead using some knowledge about what I'm trying to get. Here was minus 41. Right here I'd have minus 82. Here this would be something in the hundreds, but it ain't negative 3,000 something. So I've got a ways to go, right? So let's jump ahead to something like 80 minus 40. That's equal to 40, and 80 times 40 is negative 3,200. So sorry, 80 times negative 40, right? My A is 80, my B is minus 40. So 80 times a negative 40, we're in the neighborhood, right? It's up in the minus 3, or it's down in the minus 3,000s at least. So I don't have far to go. Okay, next observation. This thing ends in a 5. And the only way you can have two numbers multiply together ending in a 5, what do you think? Yeah. We're going to need to do something like 85 minus 45. $85 minus 45 is 40, and 85 times a minus 45 is negative 3825. Okay? So the numbers I'm wanting are 85 and minus 45. So we'll come back up here, 51x squared plus 85x minus 45x minus 75. And factor by grouping. So 51 and 85, what do they have in common? What's the GCF?
It's 1.
Is it really?
51
What is the guaranteed way that I can determine if 51 and 85 have a GCF of 1? I stressed it at the beginning of class. Some of you think that the GCF is 1.
What did you say?
The guaranteed strategy to prove beyond a reasonable doubt, beyond a shadow of a doubt, that 51 and 85, I want to know the GCF of 51 and 85. If the claim is that it is 1, then you should be able to use some kind of technique that we've discussed today to illustrate that to me, instead of a guess.
Want the first power times x to x squared plus,
Is 51 prime?
no,
How does it factor? How do you know it's not prime?
because 5 plus 1 is 6.
Because 5 plus 1 is 6. There's a famous strategy that says if I sum the digits, and the digits are divisible, and that sum is divisible by 3, then so is this thing. Yep.
3 and 17.
3 and 17. Okay. So 51 is 3 times 17. Is 85 3 times anything? No. Why is 85 not divisible by 3?
Because 8 plus 5 is not divisible by 3.
Because 8 plus 5 is not divisible by 3. Is 85 equal to 17 times anything? So the GCF is not 1. It is 17. This is the prime factorization. These are all prime numbers. This is 51. This is 85. So a 17x will factor out. And what's left over is 3x plus 5. It had better be the case that when I do the factorization on the other one, I get 3x plus 5 over here. And so that can guide you as to what must factor out. And what is it? We're looking for the GCF of 45 and 75. 15. So the minus 15 factors out. Now, I have the complete factorization of this guy. Questions? The other strategy, this is where it gets, I mean, this is already wild enough. The other strategy, what it's doing is it's finding you the solution to the equation if this was equal to 0. Okay? I now know what those x values are because I have this factor. If I said that I wanted this to be equal to 0, then it's just the same as saying that this would be equal to 0. And the two numbers that will do it are a minus 5/3 and a 15/17. X would be a negative 5/3, or it would be 15/17. Both of those numbers are unpleasant to, well, the 15/17 is very unpleasant to if I'm staring at the decimal expansion of it, to then figure out what its rational form was. It may not be obvious. But if I use that iterative technique, one of these two is going to show up. In fact, it would be this one. I could add the 75 to both sides. I could factor out my x. I could say that x is 75 over 51x plus 40. Both of those numbers that I said on the previous page, both of these two numbers right here, if I were to substitute them in for x, it really would be equal. And they're the only two that will do it. The iterative procedure that says let's have an initial guess of 2 and then iterate 75 over 51 answer plus 40 will give us one of those numbers. The only problem is recognizing it in rational form. So Here, let me do it. 75 over 5140. Is it plus 40 or minus 40? Plus 40. And I have to press this equals button like a million times. But look at this first several digits, 88235. 88235. In fact, look, it's not even changing anymore. It's just coming up the same number every time. This is the solution. But you would be hard pressed to look at that and say, oh, that's a rational number. I know how to write that as a fraction. And you can see why this particular one would be hard to do because this is 15 over 17. Like, watch, if I multiply this by 17, what am I going to get? So my claim to you is that this is 15 over 17. So if I multiply on both sides of this by 17, and it says 15 as its answer, then I was right, yeah? I'll multiply here by 17. I'll multiply here by 17. And if the result is 15, then that is the fraction 15 over 17. So, in this example, probably the strategy with the list wins. In particular, because this ended in a 5. If it's going to be some product like this that's not super easy, but has a multiplication rule. Like if you have a number that ends in a 5, it factors into something that ends in a 5. That's why I jumped straight here to 85 minus 45. Let me just look at the number 10. 10 is 2 times 5. Look, there's one of them ending in a 5. If you want to iterate and have it produce for you the 5/3, it can be done, but I'm not sure it's worth it. So this was 17 x minus 15, I think, times 5x plus 3, no, 3x plus 5. This problem, this is full grown, right? This is college algebra. They don't do this in high school, as far as I know. You won't see them trying to tackle that. Oh, and look, there we are. Just a handful of questions. So it's like easy, 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 and then pow. And that's, because you're in the blended course, you only get a 15-question homework. Those suckers in the online class have a 30-question homework. All right. This one looks deceptively simple. What kind of curve does this make? Parabola. In fact, this is a parabola that crosses right there on the y-axis at minus 25. It must do that because that's a parabolic curve that's got its vertex right at the origin, and now it just moves down 25. And if I am saying that this would be equal to 0, then you are describing the c values, in this case, of right where it takes on the y value of 0. I mean, if they would just say x squared minus 25, then it would be the x values such that we get a y value of 0. Now, this type of expression, this is a quadratic, and it's one of those special forms that I promised would be coming up all the time. What is it called? It's 4 words. Is that 4 words? It's a minus, right? So it's a difference. Difference of what? It's true, there are difference of terms, but these aren't just any old terms. It does not say this. This doesn't factor, right? Because it's not a difference of 2 squares. C squared minus 25 is a difference of 2 squares. You have c squared minus 5 squared. This is nothing more than c squared minus 5 squared. Then it will factor into a conjugate pair whose terms you already know because they're already written here. It's going to have a c and a 5 and a c and a 5. And they're conjugate, so one of them's plus and the other one's minus. Now you can go and FOIL that out, but you would be wasting your time because conceivably you had already worked on this problem like we did last time. And if you multiply those together, you get this. And the middle 2 terms add up to 0. So it's just a squared minus b squared. See the parallels here. A squared, b squared, minus. Right? The c is playing the role of the a, and the 5 is playing the role of the b. In fact, if I just say let c be a and let 5 be b, then they are identical. Then this writing is exactly the same as this writing because c is a and b is 5. The difference of 2 squares factors into a conjugate pair. We will use that. What is this, week 4? We'll use it in week 5, 6, 7, 8, 9, and 10. Just every week from now on. It'll come up over and over and over and over. And you can answer the questions really fast because you can witness what the terms that are being squared, you can see what they are. It's a C and it's a 5. This is a quadratic. Is it a difference of 2 squares? Yes. What are the things that are being squared? I want to recognize this as a something squared minus something squared. And what are those somethings? Is it just A? It's 2A. The quantity 2A squared would give me this, 4A squared. Right? Because the 2 gets squared and the A gets squared. That makes 4A squared. And then what about the 9? I am looking at the things that are going to go in my conjugate pairs. It's a 2A and a 3. Here's a 2A, here's a 3, here's a 2A, and a 3. Make them conjugate by having one be positive, the other be negative. That's the answer. Questions? Back to this guy, or this type. This is still a quadratic. But this will be what's called a perfect square. How do you want to get the answers? Should we use the A times B stuff or do the calculator? A times B. Then we want two numbers that multiply together to give me what? And two numbers that add together to give me negative 8. Okay. Candidates for A and B. 4 and negative 4 add up to 0. Negative 4 and negative 4. Oh, you're just going to jump straight to the answer, aren't you? Because negative 4 times negative 4 is, whoa, 16. Negative 4 times negative 4 is 16. Notice that they're both the same number. A and B equal each other. You can certainly rewrite this thing if you want. But after you finish factoring by grouping, you'll see that what you get is this. And then you will remember, oh yes, Mark said that if the leading coefficient was 1, then these numbers that I get for A and B, those are just the ones that go there. And then this is called a perfect square because the roots are repeated, those terms are repeated. It's just this. Like, I'm going to type that in for my answer. And we know that that's a parabolic curve. But now I know exactly the value from the horizontal axis. It's like this is the c-axis. I know exactly the value on the horizontal axis where it crosses. It doesn't cross this time, it just only touches it. It can't cross because it's a parabola. It's doing one of these numbers. It goes down and it comes back up. If it crossed it, then it would have to cross again somewhere else because it's going to have to come back up. So then this is as low as it could go. It's just going to touch it in that one spot, and that number has got to be 4. That number has got to be 4 because 4 minus 4 is 0. Questions? Another quadratic. I can't do factor by grouping because it doesn't have more than 3 terms, even though the GCF is only 1. I can use the calculator technique. I can use the method of the A and the B. What should we do? Then what should A times B be equal to? Say what? Negative 14. Because it's negative 2 times 7. And then A plus B, negative 13. I need some candidates for A and B that add up to minus 13. But their product has to be negative. So exactly one of A and B also have to be negative. Negative 14 and 1 adds up to negative 13. And once again, we've knocked it right out of the park because we got the answer on the first try. So now we know how to rewrite our quadratic. 7w squared minus 14w plus w minus 2. Now I can factor by grouping because the GCF is 1 and it's got more than 3 terms. So from the first pair, I'll factor out a 7w. And I'm left with what? W minus 2. And what factors out of this next pair? I'll always want to factor out their GCF, no matter what it is. And what is that GCF? 1. You see the difference between saying nothing and this? Because now I can witness this 1 here. And I can see that each term has the w minus 2. Now the w minus 2 factors out. And I'm left with 7w plus 1. And that's it. Questions? All right. Study this thing. Tell me what the first step should be. Where are you getting those numbers? Okay. Should that really be, should I launch off right away and do that? Does this thing have a GCF of 1? Because I only want to do that for quadratics with a GCF of 1. If there's some way to simplify it first by just factoring out the GCF, then that's going to that needs to be my first step. A 3. If I factor out a 3, then when it comes time to do the method of the whatever, I'll be dealing with smaller numbers. It'll be easier to see what the answer is. So the first thing I'll do is say, well, this has got to be 3 times b squared minus 3b minus 10. And now I don't even have a leading coefficient. Right? Leading coefficient is 1. So if I can figure out what the x and the y are, that give me a minus 10 and a minus 3, a minus 10 for the product and a minus 3 for the sum. Whatever numbers I get for x and y, then those are the numbers that go in my parentheses. Right? Because now this guy has a leading coefficient of 1 right here. Candidates for x and y. Let me get you started. 0 minus 3. That adds up to minus 3, doesn't it? But the product is not negative 10. So what should we do?
Pick 2 of them.
Huh?
Pick 2 of them.
Pick 2 of them. Do I just pick them at random?
I mean,
You could. I could also jump off this building. It would not be the best thing for me to do, though.
2 and negative 5?
2 and negative 5. If you are stuck somehow, you could increment by 1. That will absolutely bring you right to the solution. Do you see how I'm incrementing? 0, 1, 2, 3, 4, 5, 6, all the way down? And this makes some infinitely long list. And it just happens to be that right here is the answer. Right? So if you start incrementing by 1, you can inspect if you're moving in the right direction. Because this product, you would have been getting 0, and here you'd be getting minus 4. And then now for that product, well, you've got it. It's minus 10. So now we can say what? I've got my x and y. They're 2 and minus 5. Do I need to go through the motions of factoring by grouping? I certainly can. Okay, so what are the terms? And now it's factored. And it's factored completely. Because you could have accidentally done, if we hadn't factored out that 3 to begin with, then we would have gotten something like 3b plus 6 times b minus 5. And we type it in and it counted wrong because it's not completely factored. Okay, 3 times b plus 2 times b minus 5. How should we do this one? Is the GCF 1? No. Factor out the GCF. Okay, super. What is it? Tell me some prime number that both of these have in common. 5. This one has a 5 because it ends in a 0, and this one has a 5 because it ends in a 5. You have 5 as a factor if it ends in 5 or 0. So, 20 is 4 times 5, and 245 is 49 times 5. So I can write this as 5 times 4b squared minus 49. There, I've got my GCF. I factored out the GCF. Now I'm looking at this part. Well, the GCF there is 1. Okay, good. It had better be 1, or else this thing wasn't the GCF. It was merely a CF. What now?
Isn't there a square of 2?
Difference?
Square of 2 different.
Difference
squares.
of 2 squares.
So 2 different squares.
Yeah. We have a difference, and both of these are perfect squares. That's 7 squared. This is 2b squared. So, I will say that I have a 2b that got squared minus a 7 that got squared. It pays to make this writing because if you want to just jump straight to the factorization, fine. But you risk making a mistake because where does the mistake usually happen? Here. Somehow people won't, like, they don't see right away that it needs to be like a 2b. Right? So I'm looking at the entries that go into the conjugate pair. They are a 2b and a 7. And I can make them conjugate by one of them's a plus, the other one's minus. And that's it. We are done. I graded the week 2 discussion. Yeah, so
If we were to write down 5 2b plus 2b 5 4b squared minus 4.
if you tried to type this in,
Yes.
you're violating completeness. It would count it wrong. It would probably tell you something like, your answer is technically correct, but it's not factored completely. If they did their job right. All right. On the week 2 discussion, dang, y'all did great. Right? I don't think I saw a wrong answer anywhere, which is a lot different than how it used to be. So, awesome. Let's keep it up. When you get to today's or this week's discussion, you're explaining how to find that GCF. It will only rub me the wrong way. It will just irritate me if one of those things happens that I don't like, but it won't count against you. Okay. If you need to do something like, if you need to pull out an old strategy, by all means, however you want to explain it, as long as there's no mistakes. If I'm trying to factor, 4x squared plus 8x, quite often I'll see students say, oh, well, among the numbers, the 4 will factor out, and so I have a GCF of 4, and they call the GCF 4, but the GCF's not 4, it's 4x, right? And they'll deal with the 4, and then they'll want to talk about how an x factors in. This is all gobbledygook. If it gets you to the right answer, whatever. But the smartest way to proceed is to say 4x times x plus 4x times 2. Then each of these is equal to the terms we started with. And then, just like we've been doing for all the rest of the problems, I'm able to apply the distributive property to bring it out. Okay? All right. See y'all in a week. In a week, right? I'll do it. Question? Huh? You're trying to understand it? Isn't it true? What is this? If I wanted to 4x squared. Okay, and what is this? So they really are equivalent. Now, each of them has a 4x in common. And that common factor of 4x is the greatest common factor because x and 2 don't have any common factor.
It just threw me off because I forgot the 4x. So I actually
I haven't factored out the 4x yet. What I've done is recognize that 4x is common to both of them and made the writing to illustrate that. Right? The objective is to figure out how do I find the GCF? And you're not trying to tell me, you're supposed to be like teaching some other student, right, in the video. So if we just wrote 4x and then wrote x plus 2, the student might not know how you got 4x or why x plus 2 is the other term. But this exactly illustrates both those points.
just seeing it that way.
Yeah.
Seeing it that way, it messes with my mind. Because I'm used to just factoring it and like, okay, I know I'm putting out a 4x.
Mm-hmm.
I'm used to just going ahead and putting out that 4x and right and wrong. But seeing it actually like that, it messed me up.
I mean, when a person is experienced, sure, they will just jump straight to here. Okay? But this intermediate step is the illustration of why this was the answer.
That's the part you wanted to show me.
Yeah.
Okay. I was just trying to understand it, because, like, I'm used to going to Forex to
Sure.
X, just seeing another Forex, I had to, hold on, Forex, I had to actually look at it again.
Mm-hmm. Yeah, that is the thing. If the Forex is going to factor out, it must have factored out by the distributive property. And to be the distributive property, they all need that thing. So they all got to have a 4x.
Okay.
Yeah. You all right?
Yes, I have a question about the discussion board.
Okay.
Are we allowed to do, like, can we do the video from our phone?
That's
Or-
preferred.
Oh, yeah, because I didn't know if it was like, we only could do it from our computer, I didn't know if it would like work.
No, I tried to tell you last time, but then you were like, I can't do it from my computer. And I said, no, you can do it from your computer. Look, if you do it from your phone, you record it with your phone. Here I am. I recorded it with my phone. And, okay, super. I've got my video now. It's on my phone. On my browser, I can go to canvas.westcoastuniversity.
I have the app.
Don't use the app.
Oh, I can't use the app?
It won't work on the app.
Oh, okay, so I have to go to like, okay, so I have to type it in on like Google, okay.
On your browser.
Right.
Like Safari or
Yeah,
whatever,
iPhone,
Chrome.
yeah. Mhm.
Now, you go to Canvas and you log in and you go to the discussion board and you act like you're going to make a post, right? And the dialog box opens up for the post, just like as if you were on your home computer. There is a button in the toolbar. It is green. That's the Panopto button. You click it. And when you click it, a menu opens. And it says something like, okay, you want to post a video. Do you want to upload this video? Do you want to record it? Do you want to pick it from your library? Obviously, you want to upload it.
Okay.
You say upload and you point it to wherever your video is at on your phone,
Okay.
which would be stored in your camera, right?
Okay, because there's also like a tab in like the course where it says like my Panopto videos. We don't press on that? Okay.
If you go that route, you will have problems, guaranteed.
Okay, yeah, because I've never used it before, that's why.
You will have permissions issues. You can go to my Panopto videos and upload videos all day, but you would be uploading them to your folder. It's yours. You own the video and have permitted no one to see it,
Oh, okay.
right?
Okay.
And you would have to manually go in and say, I permit these people to see it. Anyone with the link, or anyone at my school, or anyone.
Oh, it's just more complicated.
It's more complicated.
Okay, so basically.
If you go straight to here, to the discussion, and upload it here,
Okay.
it will automatically get the correct permissions. And it will be embedded right in the message. So that way when we're scrolling through the discussion board, boom, there's your video. I can see the cover image, I can click play, and it just plays right there.
Okay, so we just press on the reply button,
Yeah.
and then there should be like a green.
You click on plus on the reply button, and then you get the
Can I do it
window
now?
here.
Can I do
Yeah.
it now? See, okay, let me just check. Okay. Let me see.
Okay, while she's doing that, I had a question about the midterm.
Yeah.
I took it like a week in advance.
Mm-hmm.
I didn't do so well on it, because
Mhm.
I had to get up and leave in the middle of it. I had like 5 questions left. Is it okay? Like, what are your standards on retaking midterms?
So have you not